So this is lab4 here, okay? Let me download lab4 here. All right, and All right. So let me explain to you lab4 a little bit, guys, here, okay? Lab4 is really about, a real world control project about the lab here, okay? And we want to control a radar here. The radar should be able to respond to the like your potentiometers, which is your service input. Okay, so depending on how much you're rotating the potentiometers, there's corresponding like the rotations, the corresponding the angular momentums, angular motions of this like radar, right? So I want to model the system here, which is through this kind of diagram, right? The diagram shows that based on the particular input, which is like from your potentiometers, you got preamp here, Hall amplifiers, right? You got motors, gears, you got output. So this is the idea of this control this whole system, right? For regular control, you typically have the potentiometers on your gears serve as feedback. Essentially, the potentiometers is just encoder. Think about encoder as a P gun, right? P gun. Okay. So you got this P gun there, and as a feedback through here, and it shows it is able to. It shows it is able to. It shows able to get the basic P control. But our idea here, instead rely on P control here, we do state space, okay? So the whole idea here, you model the entire preamp, whole amp, motors, gears, right? As the state space. Then you do pole placement to do good control. Makes sense? Jackson, you interview on like a broad company?
Oh yeah, I did.
That's awesome. Good for you. Yeah, if you need the reference letter, okay?
We'll see if we get any feedback.
Yeah, that's awesome. Yeah, but regardless, right? And regardless, so what we're going to do is, is try to get the entire process as multi-state space. And the parameters related to the gun here is also here. It shows the potentiometer gun, right? So the K, K1, A, and all the stuff here, right? K, K1, K1, K, KG, it's all here, right? It's all here, okay? Right, and the question show the two tasks. Task number one to show us how to derive and draw the full state feedback controller. Okay, you have to show you're able to to draw this to calculate and draw the state space flow diagram. Okay, calculate state space, right? Derive state space, then draw a flow diagram. Number one. Number two is you want to calculate the controllabilities. We talk about today as well, right? Controllabilities. So here, right, Jackson, what's controllabilities?
Controllabilities?
Yeah, what's controllabilities?
Is that like the measuring how you measure how it responds?
Yeah, so you try to measure how the system behaves, right? And one just give an open loop. You don't even just like use closed loop yet. Open loop, how the system respond during open loop. Makes sense? That's the controllability. So I mean, essentially said how awkward my drone without any control. Just throw it, for example. Your drone is able to fly right. Oh, your drone can do anything if it open loop. And the controllability means. Makes sense? Makes sense, right? Controllability means is just like without doing any closed loop, you open loop. You see, through your drones, how drone behave. The system response given under open loop conditions, controllabilities for more serious definition. But really what we're saying here is just how system behaves in the open loop conditions. Just, that's the controllability, okay? Why controllability matters? Why controllability matters?
So you can get feedback of if what you're doing is improving it.
Yes, because we want to make sure that our system can be meaningfully controlled. If a controllability disaster not controllable, you better don't even bother to control it. Why? Because it's very difficult. It takes a lot of time and the results will be very bad. You better spend time modify your design instead do PID control, which is not productive. You spend time to do a poorly controlled system, right? And it's not controllable, right? Right? And you just waste the time. We said to you, you better calculate controllability first before you spend time to control here. 1 second. All righty. So yeah. So so you better do the calculation and controllability and first before waste time. All right. And the question number within task 1, I ask you to do another thing, right? So you want to calculating the pole placement gains. You say, oh, I want to control this radar, right? Your face, right? Your pole placement, and what's the gain I need to control it. So this is the idea of the pole placement, okay? And calculate the K, right? Task number 1. Task number 2 is I want to design observer. We talked today, right? Observer again, observer, right? I want to design observer and draw observer flow diagram. We taught exactly workflow we taught today. That's why we taught this lab here. And we already show you how to design observer from scratch, right? Remember, observer design, right, in chapter 5. And it shows you how to design the observer gain L, right? It's starting from, right, Ethan, right? Where we start from? Derive, right? Derive observer flow diagram, remember? Right? Observer the state space, right? We call observer canonical state space. First column non-zero, right? How derive it? We show explain to you, right? Derive the highest order cross multiply. We taught today, right? You say, really? Did you talk? I don't know. Yeah, right. You can go to look at chapter 5 one more time. It says, right? Yeah. Then apply that to here. In lab 5 immediately. In lab 4, sorry, immediately. And then you can calculate the L. That's the task number 2. It says, let's go today, right? Let's go today for this lab 4, okay? And of course, you have to calculate observability. Observability is similar to controllability, right? Because, I want to design beautiful filters. First of all, are you sure your gyroscope is good? So I mean, the gyroscope is literally nothing bad. It doesn't work. The gyroscope is terrible. It broke many years ago. You better not waste time to the filter because you are filtering wrong systems. It says, another way here is you try to filter something like let's say aliens, like UFO. Do you know UFO, guys? UFO. I want to filter UFO motions. You better don't waste your time. You're not able to. Because based on my knowledge, UFO motion is erratic, random, sometimes, to nuts, in all perceptions. It says you better don't waste time there. Why? Because no one can predict, I don't think. You better not waste time. Okay? There's other systems you cannot even let's say solar systems. Solar system, the motion, I know solar system motion sometimes, especially relative motion, is all like a Milky Way. and has a lot of erratic random motions. Okay, black hole motion. And you're just not able to predict. All the mathematics disappeared. It's not useful. For example, inside black holes. Do you know what's going on inside black holes? No one knows. Right? So you better do with time design the future or observe for that, right? So you have to control observability. Yes. And here, obviously, calculate L, okay? Implement observer. The last thing here, everything we need to simulate use MATLAB, okay? Our provided code. Sound good? So let me walk you through a little bit for the stuff here, okay? So I do have a solution here, okay? So let me show you the solution here, okay? Right. Let me explain to you before you say, oh, I don't know for that. I'm not quite sure. All right. So the step number one is GS. That GS representing the transfer functions of the system, correct? Yeah, Melissa, we talked about this like the lab4, right? So this GS is transfer function of the system. You see how you get that? You get that is from here. You get it from here. So it's essentially is through this multiply here. You multiply everything here, right? You multiply it. You multiply these terms, this term, right? You see what I mean? Yeah. Sounds good. You multiply that, right? Multiply that, and then you got your the transfer function systems. The transfer function systems, it just look like this one here. Just do this one here, right? And as we know, based on transfer function to get state space, there's many ways, right? Here, we use phase variable way to derive the state space from transfer function. Here, right? And Ben, do you remember how to derive the transfer function? How to derive state space from transfer function, or you based on phase variable? Huh? Yeah, derive the state space based on transfer function. Yeah, how do that? Yeah. Right. So yeah, so this one here is your first of all, this is the original transfer function, right? So based on that, here, let me show you the process here, okay? Yeah, so let me show you one of the examples. Yeah, I understand. So sometimes we forget this one, right? Based on the topic one. Right, let me see topic one. Let's see, hopefully get one topic one here, right? Cascade, phase variable, parallel. Yeah. You cross multiply, right? This is a control canonical, almost similar to the phase variable, okay? Phase variable slightly different, but not too much difference. I think here this control canonical, let's see. Yeah, phase variable. Yes, this is exactly the one we're looking for. Phase variable. Go to topic one, right? Topic one, go to slide number 18. Topic one, slide number 18 shows the entire process. How you derive the like a state space based on transfer function. First, cross multiply, right? Second, right, substitute, right? Replace variables, right? Replace the variables. S1 is C1 here, right? S2, SC1, S3, S square C1, makes sense? So because this C1 S square, right? So C1 S square become what? Right? C1 square become S2 dot, right? Right? SC1 become SC1 become S2. And C1 here become S1. Essentially, we said S1, C1, S2, SC1, S3, S squared. Sense is S2 dot. Makes sense. Replace variable. Why? Because you have to. There's no S1, S2, S3 here. You have to go back S1, S2, which we used to here, right? It says, yeah, you replace the stuff with this and substitute back here, right? You got two equations. You got two equations, right? You got two equations, and then you got your state space. Makes sense? The typical way of the is your phase variable. The second row, right, for 2 by 2 is non-zero, which will fit better. Sense? Right? Isn't it right? Yeah, this is the way. This is the way. But you apply similar way to this this like transfer function, which is here. You apply similar way to here. You got this, and the details you have to go to details by yourself. Okay, by yourself, and then you got this like the state space. Look, let's say state space here. The first row, second row, and the third row, right? And this your non-zero terms, which are open loop non-zero term, right? And S1, S2, S3. Why 3 by 3? Because look, a transfer function to denominator, third order, right? 3 orders, makes sense? The highest order, third order, okay? And you got 3 by 3 matrix, which is open loop. Matrix A, matrix B, matrix C, okay? Right. You got A, B, C matrix here, okay? Once you get A, B, C matrix, it is do contributivity. Contributivity is B, A, B, A square B, okay? B, A, B, A square B, okay? And then you can calculate the contributivity through determinant. Through determinant, okay? Through determinant. And you calculate determinant, it's non-zero. Determinant non-zero, right? You calculate determinant is non-zero, right? If determinant non-zero, what it means? If determinant non-zero, right? What does it mean? What does it mean? If determinant non-zero. Yes, it is controllable. If determinant non-zero, that's controllable. If determinant is zero, it's not controllable. Okay. All right, and then you you follow the same process. You find like the full step feedback, the K1, K2, K3, right? How we find that? We can determine, right? Determinant. And the determinant is, A must be K here, A must be K da da da. You right, then you can determine that, right? You can find your there. You based on this, you can find the damping ratio, find the frequency. You can find the desired curve equations. Your desired curve equations, right? Your desired curve equation, because remember, this is 3 by 3 matrix. You have not only K1, K2, you have to not only the 2 poles, you need 3 poles for desired curve equation. Then you need to create the third artificial pole for you. The third artificial pole here is right there, okay? It's right there. Yes, this is a third pole here for you, okay? Sorry, this is the first, second poles. The third pole 10 times faster, okay? Typically, third pole is larger, 10 times, right? Yeah, so you got like the third pole there, and then you this is a desired curve equation, okay? This one here. Let me highlight it for you, okay? This is your desired curve equations. This is your desired curve equations. And your system equations is calculated determined Si minus MIBK, correct, guys? Remember? Determined Si minus MIBK, that's your system equations. And you calculate that determinant, that's what you get. This is your system equations. Then you match between system and desired, you get the K1, K2, K3, which is your hole placement gains, correct? Right? Hole placement gains, which K1, K2, and K3. You got three different gains, right? You got three different gains. Once you got three different gains, right? That's the finished part one, right? Then you got the part two, right? Part twos. The part two is the way you got part two here is the first one, right? Observer design, right? The first thing first, you check observer design, do observability, right? Observability is you got A, right? You got C, remember? A minus LC, right? A minus LC, right? For doing observer design, right? But check observability inside B, A square B, right? You got C, CA square. Right? For contributed the B, A square B. And this one here is C, CA square. Makes sense? CA square. So that's for observability, okay? Observability. You got the B, A square B for contributed. This is observability, CA square. It's a column, okay? It's columns. Yeah, so you got this you got the observability, you do the mission application, and this got determinant. And apparently there's observable, not observable. Observable, not observable. Determine non-zero, right? Yeah, determine non-zero, right? So I think it's observable, right? If you determine non-zero, you got observable here, okay? You got really observable here, right?
You're checking on
Yeah.
3 weeks until the end of the semester.
Yeah, so you got observability here, right? So observability, this is determined non-zero, right? Because the determined non-zero, you can because determined non-zero, right? And you can is observable, okay? Observable, makes sense? Observable. And so now we know observable, we know it's controllable and observable, right? So now is a good time to count L. We taught today, okay? And L is done by a similar process as done today, okay? First, you need to calculate the like 10 times faster. Why? Because observer, remember, observer has to be 10 times faster than controller, okay? Right? Than controller, makes sense? Right. So that's observer design, okay? So so you got the pose there, okay? You got a pose. You got a pole there, and you got a pole here, right? You got a pose, and so this is your like you got remember. So this 10 times faster, your natural frequency, right? Natural frequency has to be 10 times faster, right? And you have to recalculate the pose. Recalculate the pose. This after recalculate pose. This is the pole here, okay? And this after that, right? You got the third pole, which 10 times faster, right? You got net 200, right? And then observe canonical, and this how to observe canonical member divided by highest order, right? Divided by highest order, right? And you got the first order grouping. You got a first order grouping, second order grouping, first order grouping, second order grouping, third order grouping. Okay. Based on the grouping here, right, you can derive like you can derive the your observer form here. Okay, observer forms. And remember, you have to add as two term. Sorry, you have to add as two term here as three terms. Why add that? Because the flow diagram, it has to be there. If not be there, flow diagram cannot be true. Remember Ben, right? Remember that, right? You have to add as two term as three terms. Once you add as two term as three terms, you can easily make this this observer state space. Is observer canonical. Observer canonical form state space, okay? Which is this. And then you got A minus LC, right? You got A, B, you got A, B, C, right? A minus LC, right? You got A minus LC stuff. You got A minus LC, is this, right? You got A minus LC there, right? And you got this one here. Once you get A minus LC, and you can easily calculate the system curve equation. Why? Because you can do the system curve equation. And actually, you can this one actually from determinant what? Remember? I remember. What's that? Si minus what? A minus LC. It says, but you can actually mapping directly from this one here to here. This one here to here. This one here to here. It says, right, and you got signal curve equation is this. And then you got desired curve equation, which is this, right? You got desired curve equations, desired characteristic equation. You got system equation, which is this. And then you match it. You solve L, okay? Match to solve L. Great. And then you solve L. Let's end this solution step. But that's not end the whole thing here, okay? We need to here is run the mathematical simulation. For entire thing here, we have to run the simulation here, right? So let me say here, we can run simulation here, okay? The code is here, okay? Let's go to the lab here. For see this code, you have all the code. You have observer code here, right? You have the main code, which has main logic. You have like you have the controller. This is question number one. Full state feedback control, right? This is number two, observer, okay? Let's see whether we can go to MATLAB math. Typically use online, right? Mathworks.com, okay? I don't typically use like a local anymore, right? Just go to mathworks.com, see whether I still can log in, okay? Hopefully I can demo to you, okay? Yeah, I can log in. Open MATLAB there. Yeah, MATLAB online, right? Really good. It's really beautiful, by the way. So class here, da, 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 da. Yeah. So you got the main code here, right? Which is this. You run here. You got the full step control, right? Full step control, right? Full step feedback control. Yeah. So this is full step control, right? You can run it. You can see, right? You can see, guys. So that means the full step feedback control actually works. Why actually works? Look here, right? Look here. So the full step control here is, you can see this one here is your like it is your like the step input, right? And this is your step response. See what I mean? I mean actually you can control, right? Although there's a pretty big steady state error, right? See what I mean? That's the problems about this like full step control, full step control, because it does not consider integral part, mostly PD control, by the way, because it does not consider output. You did not bring back the output. You say, really? Are you sure you not bring back output? Yes. You actually can look at from mathematics here. So there's no from here, right? You see, you guys, you see that, right? Based on full feedback control, did you say based on full feedback control, right? Did you say output here, right? No output, see? Output not feedback. You only feedback this part. Output is not fully feedback. Okay. This is observer. Observer is, and you can show here. You can see full feedback here. Full feedback here, right? Look, you only considering this part. Only feedback state. There's no like a y part. Y was not feedback there. Sorry.
I'm sorry, where?
The A.
Yeah, the A. So the 171 or 101 of both.
Are you talking about in the matrix?
Yeah.
Yeah. 0, negative 471, negative 101.7.
Oh, in the X dot?
Yeah.
Okay, yes. Yeah. That whole matrices is A.
Right.
Just following that X dot formula. Because then B is the 0, 0, 1. And then
Yeah.
A is the matrix K1, K2, K3.
You say the y part not feedback, right? Only x feedback. That's why I call full state feedback. The y is not feedback. That's why you have integral control error. And there's a pretty big error between the your input and output. You see what I mean? The input is this. Your output is like that. A huge error there, okay? But it's definitely stable, right? It's not like diverging, right? It's stabilized. Right. So that's one, right? Now the second one, if you run this observer, this observer, right? You run observer, if you run observer, right? If you run observer, you can say, look at observer, right? For observer here, is any big difference between the observer looking and the full feedback, or not much difference? Is anyone can see difference there or no difference? The difference or no difference between observer and this like the
It's about the same.
look about same, right? You see, that's exactly what observer do. Observer discover your ground truth. You see what I mean? The ground truth. Essentially, what's the actual like the whole placement do, right? Observer will be just like a discover truth. It's actually replicate what we do. You say, oh, really? I don't see any use. It's just replicating, right? Remember, that's given without noise. If with noise, and this thing can still recover that. If you can try it with a little noise, right? It's still able to, you can add noise, link. You can add no link, and the observer is still able to reconstruct the ground truth. That's the beauty of observer, okay? But this is why we didn't add noise. You can add noise. You can add noise here if you're interested. Oh, really? I want to see it. Yeah, you can add noise. You can add noise here, right? You can add noise around here. You actually can see the observer still able to give that beautiful curve. Okay, that's why observer can denoise. It can denoise. Because observer is pretty beautiful, right? It can reconstruct your beautiful truth there. Okay. Yeah. So that's observer. And the third one not required. I do have integral control here. This is integral here, right? So look, integral we can talk a little bit next Tuesday. Okay, next Tuesday we can talk integral. Look, we did not talk yet. What's integral control? Integral control essentially you bring back output, input. See what I mean? Integral control essentially just full feedback. Only difference here, you have a K here, right? And a KE. KE is the integral part. We call integral control. Remember, what's the purpose of integral control? What's the purpose? Right. Why we can do that? Because we bring back output. You have to input adding AE. You see what I mean? Integral control, right? And you can see that actually with integral control, right? This space, right, become very. Look here. Oh man, look at that. Is that great? Is that stays the arrow? Not much anymore. Right? No, right? Almost none, right? You see? State space is the integral control, right? Remove the steady state error, which exists for full feedback control. Make sense, guys? Does it make sense? Error makes sense to you, right? Error makes sense here, right? Is that clear? Is it clear, guys? I think it's pretty interesting, right? Yeah. So so this is end of lab 4. Okay, and lab 4 this is pretty much. Again, the integral control I didn't ask you wrong. If you wrong it, that'd be beautiful. You can say, oh look, full feedback control has a big error, especially to do with the steady state error, right? But integral control is able to remove the steady state error very, very efficiently. Okay. The observer just reconstruct the plant really well. Okay. Alrighty. So this is about the conclusion of lab 4. Okay. Thank you.